Welcome to Maths with EJD. I've been taking a series of classes on basic calculus. And the last video in this series, I talked about limits of functions of real variables. And of course, in the second, of course, for the second module, right, it is supposed to be about limits and continuity of functions of real variables. So I did limits so that the in one video, and I want to continue with continuity now, so the video doesn't get too long. If you have not subscribed to this channel, feel free to do that. Don't forget and press the bell button, the notification button, so you can get alerted whenever a new video is released. So let's go ahead and talk about continuity of functions of real variables. Now, interestingly, you discover that everything we've been learning is a build up to the next thing. Like we talked about graphs and functions of real variables. Now you see how graphs and functions, graphs helped us to understand limits. And now we are coming to continuity. And you see that in continuity, we need the idea of limits to actually understand continuity. So it's a build up to every new thing we learn is a build up to the next thing. So let's go. What is continuity of functions? Continuity of functions, right? So continuity, first of all, is of interest because we need to ensure that functions are defined for the given range of the dependent variable under consideration. So you see, functions can be represented in different ways. You can actually have something like this. You can have a function behaving like this. A function can go like this. So it's continuous, no break. But then you can have a function like this. It has a sharp bend and then it comes down. There's no continuity here because of this sharpness. Then you can have you can have jumps. So the function goes and then it jumps and then it continues from there. So there's no continuity around this place. There's no continuity around this place. But then if it flows freely like this, then you say it's continuous. So that's the graphical way to talk about this. And that kind of idea is very important in mathematics so that you don't get to a point and then there's a breakdown. That's why continuity is of importance. Continuity is of interest because we need to ensure that functions are defined for the given range of the independent variable under consideration. So of course, talking about x now, if you come to this point, you can see the function is discontinuous around here. It's discontinuous here, but then it's continuous everywhere here. Okay, so let's go on to slide 31, where the next idea is. Okay, so let's talk about rational functions. Most of the times, rational functions have discontinuities because of that division under, right? Because, whenever we say f of x for a rational function, right, is equal to p of x, say p of x over q of x. The reason why we always say that q of x must be unequal to 0. That the reason is because at the moment where q of x becomes 0, then the function is undefined. That means undefined means that the function is infinity. That's why that clause is always there. So generally, rational functions are discontinuous at the points where their denominators are equal to 0. So for this now, you have a rational function. Anywhere this function is equal to 0, then the function will be discontinuous at that point. So for instance, the points of discontinuity of f of x equals x squared plus 5x plus 6. In this case now, we just can be obtained as follows. So just if you want to find the point of discontinuity, just equate this to 0. So you have x squared minus 4 equals 0. And previously I told you about difference of two squares, where a squared minus b squared is the same thing as a plus b, a minus b, or if you like, a minus b, a plus b. So that means you have x minus 2 plus x plus 2, which is equal to 0. So x minus 2 equals 0 means you have x equals to x plus 2 equals 0 means you have x equals minus 2. So as such, the function f of x, which is equal to x squared plus 5x plus 6 over x squared minus 4, is not continuous at x equals plus or minus 2. Or you can say the function is discontinuous at x equals plus 2 or minus 2. So if you are told to find the point of discontinuity of a function that is rational, just equate the denominator to 0 and solve for x. Then in the same way, if you are told to find if a rational the point where a rational function will be 0, in that case, equate the numerator to 0 and solve for x. So in this case now, this function will be 0 at minus 2 and minus 3, but it will be discontinuous, it will be undefined at x, wherever x squared is minus 4, which is minus 2 and plus 2. So if you are told to find that the values of x for which a rational function will be 0, equate the numerator to 0 and solve for x. If you are told to find the point where the function will be undefined, or you equate the denominator, the base, the bottom rather, to 0 and solve for x. Okay, another issue, another place where you can have discontinuity is when you talk about step functions. I think I talked about it under limits, that a step function has different is defined differently within different intervals. So furthermore, step functions are usually discontinuous as they are defined differently for certain ranges of the independent variable. For instance, the function f of x equals, so this function now is 2x minus 1 wherever x is less than or equal to 2, but it is now x squared plus 1 whenever x is greater than 2. So in this case, now you see that at 2, there's a jump, there's a change in definition of the function. So at x equals 2, there will be a discontinuity in this kind of function because it doesn't flow smoothly. So this function has a jump at x equals 2, that is, it is discontinuous at x equals 2. For you to get a better picture of this, can you just see the picture of this function now? So this is the step function. So it is 2x minus 1 when x is less than or equal to 2. So this is 5, right? 1, 2, 3, 4, 5. So it's 2 around here. So less than 2 is this way. So less than 2, the function is defined as a straight line, which is 2x minus 1. But greater than 2, the function is defined as x squared plus 2. So greater than 2 is to the right. And then it becomes like this curve going up like that. So you see that around this place, there's no continuity. There's a jump. There's a space there. So you have discontinuity mostly happening for rational functions and for step functions like this. Okay. So how do we define continuity? A function f of x is said to be continuous if, so there are three conditions, and the three conditions must be met. First of all, the limit of f of x as x approaches 0 exists. Exist means that it is not infinity. Then the next thing is that when you evaluate the function at a itself, that is, you put a into the function directly and you get, so the answer also exists. That is, it is defined, not undefined. And the third condition is that this limit that exists is exactly the same thing. It's equal to f of a, which also exists. So that's the third condition. So the limit exists. The function evaluated at the value towards which x is tending also exists. And then the two of them are equal. So those are the three conditions for which you say that a function f of x is said to be continuous. Okay? So let's look at this example. So you want to investigate the continuity of f of x, which is x squared plus 4x plus 2 all over x plus 2 at x equals minus 2. So is this function continuous at x equals minus 2? That's what the question is about. Is this function, this rational function, that continuous at x equals minus 2? So what you do is you do the three conditions. The first condition is find the limit of the function as x approaches minus 2. And what do you do when I say, whenever you have limit, the first thing you do is substitute directly, right? So put minus 2 wherever you see x. So you have, of course, we can factorize, right? We can have limits. So I'm not even substituting here. So I have limits as x approaches minus 2 and x squared plus 4x plus 4. You can factorize that into x plus 2 into x plus 2 divided by x plus 2. So one we cancel out. So you have limit as x approaches minus 2 of x plus 2. Then you can put minus 2. So you have minus 2 plus 2 equals 0. So it means that the limit as x approaches minus 2 exists. So the next thing is you evaluate, limit does not mean that the value of x is minus 2. So, and in the same way, it does not mean that this function itself is 0. It only means that as x is moving towards minus 2, the function is moving towards 0. It's not actually at 0. Okay? And then the next thing is f of minus 2. F of minus 2 means you're actually, so now x is actually 2. X is actually minus 2. And then the function is actually whatever the value ends up becoming. So f of minus 2 means that you put minus 2 into the expression. Again, we can break this down. So we are evaluating at x equals minus 2. We break this down and this cancels out. So you have x plus 2 evaluated at minus 2. Then, of course, f of x evaluated at minus 2. I know that is equal to, this is x. So that's minus 2 plus 2. And the answer again is 0. So you can see that the limit exists and it is 0. Like I told you, 0 is a good answer. It is only infinity that is a bad answer. So here too, when you evaluate the function at minus 2, you also get 0. So the first two conditions have been met. And then, interestingly, the two values are actually equal. So you see, this is the summary of the three conditions in one sentence. So the limit of the expression is equal to the function evaluate the limits of the function as x approaches -2, and the value of the limits when you evaluate it at -2, and they are both equal to 0. So if that is the case, you can say that f of x, which is equal to x squared plus 4x plus 4 all over x plus 2, is continuous at x equals -2. Since the limit and the limit evaluated at the limit is 0, the function of the function, the value of the function evaluated at -2 is also 0. So you can say that this function is continuous at x equals -2. Okay. So we go on to the next slide, which should be 36. Yeah. Okay. I mean, this just shows you that, of course, this function is rational, right? It is actually continuous. Although you know that you see x plus 2 down there, right? And it looks like when x is equal to 0, when x is equal to -2, then there should be a jump. That's around here. Normally, there should be a jump. This is where you have -2. That's -1, -2, -2, -2. So you should have a jump. But you know why? This x plus 2 can cancel. You can factorize this as x plus 2 squared. That's x squared plus 4x plus 4 divided by x plus 2. So this cancels this, and you have x plus 2. So x plus 2 on its own is continuous. That's why you have the function as actually a continuous function. Okay. So we have this other question. Interestingly, it's a rational, it's a step function. Like I told you, a step function is a function that has different definitions within different ranges. So you have this question, it's f of x, which is x squared minus x plus 1 whenever x is less than 0, and it is sine x whenever x is greater than or equal to 0. Is it continuous at x equals 0? That's our question. So let's see. So you have limit of f of x as x approaches 0 from the negative side. Negative side means when x is less than 0. So you have limit as x approaches 0 from the negative side of x squared minus x plus 1. And that is, so you put 0 now. So that's 0 squared minus 0 plus 1. And that is 1. Nice one. And then what about from the positive side? Don't forget, one of the definitions I talked about limit is that a function only has a limit if the limit as x approaches a from the negative side is equal to limit as x approaches a, as x approaches a, as x approaches a on the other side. So then you have so in this case now, from the positive side, you discover that from the positive side, this point, you have x greater than or equal to 0 and sine x. So when you put 0 there, you end up having this particular 0. So sine 0 is 0. So with that alone, the law has broken down. So you see that the function of 0, for the limit alone, the limit does not even exist, first of all. So, but then if you evaluate the function at x equals 0, it actually does exist, it exists. But then this one, the limit does not exist, but this one exists. So at the end of the day, the function is discontinuous since the limit of f of x as x approaches 0 from the negative side is not equal to the limit of f of x as x approaches 0 from the positive side. Okay. So, and then look at what the function looks like. This is the step function now. So for x less than 0, that's on this side where x is less than 0. So look at what the function looks like. But around here, there's a jump. Around all this side, there's a jump. But then on this other side, you see how that goes. So it's another thing entirely. So you can say this function is actually not continuous. The function is not continuous. Okay, so this is shorter than limits. So, and at this point, you have some exercise to try your hands on. Discuss the continuity of f of x, which is equal to x squared minus x as x less than 0, and sine x as x greater than or equal to 0 at x equals 0. So is this function, this step function, is it continuous at x equals 0? Then number 2 is x squared minus 1 all over x squared plus 1 continuous at x equals -1. This is the second one. Then investigate the continuity of x squared plus 1 all over x plus 1 at x equals -1. So try your hands on that, of course. And if you want to get how I plot my graphs, you can think of Desmos. Desmos helps you to plot nice graphs. And of course, you can read more about the idea of limits on Wikipedia and other platforms like that. Again, if you have not subscribed, please do that. It will do you a lot of good. And don't forget to press the notification bell so you can always get alerted whenever I upload a new video. See you in the next video. Thanks for listening.